is it a knot or not? By the way, if it's not a knot, it's called an unknot. And that's what we're going to be talking about now. An untidy pile of string, maybe your headphones. Is it a tangle, or is it a load of knots, or is it an unknot? And the reason we're talking about this is that actually mathematicians spend quite a lot of time thinking about knots. It is, as you will hear, a very important problem. And our next guest has just made an important breakthrough in analysing knots. He is Marc Lackenby. He's Professor of Maths at the University of Oxford. Joins us now. Marc, you're going to have to take me very gently through this. But can we begin with this really interesting idea that your research begins with, the idea of the knot and the unknot? So what is the importance of an unknot? We've got to get this concept clear first, don't we?
Yeah, right. So, hi. A knot it's just a piece of rope, basically, which you kind of tie up in some way, and then you glue the ends together and it forms a closed loop. And it's called an unknot if you can deform that back round to a round circle.
Right.
And, everyday experience says that some knots are knotted and some knots are in fact the unknot. And the problem that I've been able to solve is to get a computer to be able to decide efficiently whether a knot is or isn't knotted.
Right. And so if we had a sort of just a pile of rope and we were to take the two ends, put the two ends together and lift, if it's a circle, then it's an unknot. And actually, it's kind of like more of a tangle than a knot. But if it's got over crosses, then it's a series of knots. Am I right so far?
Yeah, that's right. Yeah. So it might have a series of crossings, but maybe you can undo those just by twisting the knot around to get it to the round.
Of course. I'm thinking of my garden hose at this point as well.
Exactly,
Everyone's got a different thing in mind, I'm sure. Now, the very idea of expressing this mathematically, I'm sorry to say, goes beyond the ambit of a 4-minute interview. But you are doing the maths. You've got the computer to look at this and just tell us, why is it important to be able to identify quickly whether it's just a tangle and an unknot, or if it's actually a series of knotty crossings?
Yeah, well, I mean, so it's for a start, it's a famous unresolved question whether this could be done efficiently. So sort of mathematicians, we set each other sort of problems, and this one has been a really long-standing one. It's been around for over 100 years. So in some sense, there's just its own intrinsic interest. But actually, knot theory generally has lots of applications. So, for example, our DNA is knotted. And understanding the way that it knots is actually kind of important. So, for example, when the DNA in our cells, when it replicates, when our cells replicate, the DNA has to unknot itself. The way that it does this is not fully understood. But in fact, many antibiotics work by blocking that in bacteria. They block the ability for DNA to unknot itself, and so the bacteria can't replicate and they die. So knot theory has lots of applications beyond just pure mathematics.
Oh, I didn't know that. And so with the maths that you've come up with, a computer and therefore scientists can analyse faster the nature of the tangles or the knots in the world around us, be it at the micro level of a cell, or I imagine great loops up in the universe, in the stars as well.
That's right. So in fact, yes. So sort of knotted vortices in the flow of plasma within stars is another thing that scientists study. Yeah, so before there was this sort of fundamental constraint that basically there was a limit to what could be studied by a computer because like each time you added on a crossing onto your knot, all the previous techniques for studying this, the amount of time that it took doubled.
So you've basically helped the computer understand the knot more. What an achievement. Marc Lackenby, privileged to have you on, Professor of Maths at the University of Oxford. Thank you to Marc.